Gaussian. And we looked at this, and we found that if you look at the mass ratio of like the vertical vectors, it looks like the objects in the Gaussian path prefer to merge with other objects in the Gaussian path and not with objects in the path. Right? So one interpretation is that there are two populations in two distinct places in space. You know, maybe one of them is in the halo, one of them is in the disk, in which case the one in the halo could presumably be from a black hole. I don't want to insist this from multi black holes because there are like a dozen other explanations which I quickly put in the paper, but it is possible. Okay, so this is my contractual advertisement that multi black holes are a kind of anyway, let me go back to Lyman-alpha forests. So this is a talk about the PRIYA simulations, which are named after my wife, who is pictured there. It is a good idea to name the simulations after your wife. The code is public. So what is Lyman-alpha forest? So the Lyman-alpha forest is a series of absorption lines from neutral hydrogen in quasar spectra. It traces. Oh yes, that should be all there. Oh.
It's so high. Oh, I muted it before I gave it to you.
Oh, you muted. How do I turn it on?
Can you hear me now?
Yes.
Simon? Yes, great. Okay. Well, you missed an amazing joke that I made about a lot of things. Probably the funniest thing you'll hear all year. Okay, so right. So what is Lyman-alpha forest? The Lyman-alpha forest is useful because it traces weakly nonlinear dark matter structures at a redshift of about 2 to 5. And this is a picture of the sight line going through dark matter, and this is a picture of the absorption that you get as you go through the dark matter. And you can see that the overdensities here kind of line up with the overdensities in absorption. They don't line up exactly because there's a peculiar velocity that redshifts the absorption a little bit. Why is this useful? So I think Kira is sitting in the back. Yes, so I would like to advertise a paper of Kira's, one of our wonderful organizers in this conference, which uses this to constrain axion dark matter, right? So this is useful because it probes overdensities in the dark matter before virialization. It doesn't really probe virialized objects because they saturate. Because it probes overdensities before virialization, it's able to measure small scales without the signal being washed out by baryonic effects. It also probes high redshifts, which again helps because structure is less nonlinear at high redshifts. So redshift 2.6 to 4.6. And it probes these small scales. These are the native units of the forest, seconds per kilometer, which are velocity units. And these are how they roughly translate to physical units. So 0.1 co-moving h of a megaparsec is the largest scale it probes, and maybe 3 to 30, depending on the data set you use. Okay, so this is useful because it probes very small scales and very high redshifts. So what have we done here? We have run the PRIYA simulations. So these are, before I go to my movie, these are roughly 50 simulations with 2 resolutions. I'm calling it a low resolution simulation. This is roughly the resolution of the illustrious simulation. I've run maybe 50 of them. These are full hydro simulations with all the galaxy formation models that you might think about. It is in fact, it's the asteroid galaxy model. It has black holes and AGN feedback in. We also ran 3 higher fidelity simulations, 3 higher resolution simulations, which is able to correct the resolution of the relatively low resolution simulation suite. I've said here that I've run 50 illustrious simulations. You might think, hang on, how did you do that? Surely illustrious is a big project. The answer is that I was able to do this by cheating and only running it to redshift 2, which is all I need for the forest, right? So redshift 2 is a long time before redshift 0, so this takes a lot less time than you would need to do it all the way down to redshift 2. Here is a movie. I can make it big. So this is a sight line going through a simulation box. Ooh, it's lovely. Look at that. Isn't it wonderful? So it's such a big box. It takes a long time to go all the way through. Such a beautiful movie. Although obviously not as beautiful as my wife, which is named after. I get it back again. Yes. Okay, so what do we do with this? So we extract about 1 million sight lines from every simulation snapshot. They look like this. We Fourier transform the absorption along the sight line, and we take the power spectrum. And then we average over each over all the sight lines, right? So what this does is it effectively integrates over two angular directions, mixes modes, which is kind of annoying, but we get then this summary statistic, the flux power spectrum along the line of sight of the quasar. Why do we have 50 simulations? We have 50 simulations so we can have 50 different cosmologies. So what we've done here is we've run 50 simulations with a different cosmologies in some high dimensional space, and we build a Gaussian process interpolator, which is able to output a flux power from a cosmological simulation as if it had a 120 megaparsec box, 3,000 cube particles, and some arbitrary cosmology within our simulation grid. Okay, so you can think of the PRIYA simulations as a black box that outputs a Lyman-alpha forest with the cosmological parameters that you want, essentially. We have to specify specifically what cosmological parameters we want. This is the specification that we've had. So we have some amplitude and some slope. Notice that the scale on which I'm measuring this amplitude and slope is 0.78 megaparsecs, which is somewhat smaller than the scale on which you normally measure the amplitude and the slope. So these are the same as the CMB parameterizations, but on smaller scales. Right. This will eventually, this is a primordial power spectrum. It turns into a linear theory power spectrum with some transfer function. You can think of what the forest is doing as measuring this linear theory transfer function multiplied by some nonlinear response function and adding in some transfer function for the gas physics. Okay, so if for the high energy theorists, this is what you should think of what I'm actually doing. Okay, and the gas transfer function could include some baryonic physics, right? But if we understand the transfer function well enough, we don't need to care exactly what the baryonic physics is. However, we do have some new gastrophysics in PRIYA. So the new gastrophysics that we have is models for reionization, specifically hydrogen and helium reionization. These are models that are inhomogeneous. They have large ionized bubbles throughout the simulation box, and we vary the free parameters of these models and marginalize them out in the simulation suite. So, part of the point of this simulation, of this talk, is that you shouldn't, if you're a high energy theorist considering getting into the simulation field, you shouldn't be afraid to get into hydro simulations, right? Like they're not that much worse than dark matter simulations. You should be a little bit afraid because you'll run your simulation model and then something ridiculous like helium reionization will turn out to be important, right? But you shouldn't be too afraid. It's not that bad. Try it. It won't be easy, but you can do it. Okay, so I don't want you to be afraid of this slide too much. Okay. But you should be a little bit afraid because it turns out that the parameters of the helium model are degenerate with the primordial power spectrum slope that we hope to measure and open up the error bars quite considerably. So let me just summarize roughly what we did. You pick some parameters to simulate, you run a whole bunch of simulations. All the codes to do this are public. You generate some mock Lyman-alpha spectra, you run it through an interpolator. From the perspective of someone wanting to analyze a model, this is a black box. You write a likelihood function with some existing data that some observers have spent a lot of money making, and then you get some parameter constraints on cosmology. Okay. This is the answer that you get out. In the 20-minute version of the talk, I want you to ignore all the chains except for the red one. So the red one is our final cosmological parameters. These are the numbers that we get. So the power spectrum slope is like 0.983, sigma radius like 0.7. This is a parameter that's roughly equivalent to galaxy bias in the forest, and it's consistent with prior measurements. So that means that you should believe me. Notice that how am I doing for time? Notice that the slope that we get is 0.983. The Planck slope is 0.965, right? So within the error bars, our measurements are consistent with Planck. This is nice because this is the first model of Lyman-alpha forest which measures a slope which is consistent with Planck. So this is great. Also, the models that solve the Hubble tension by increasing the slope, you will notice that this error bar kind of goes up, right? So the models of Lyman-alpha forest, the models of cosmology that solve the Hubble tension by increasing the primordial power spectrum slope are no longer ruled out. Okay, so I've made things either worse or better for high energy theorists, depending on your point of view. I do have a low sigma h, right? So Planck wants a sigma h of about 0.8, I get 0.7. This is about 3 sigma lower. This is conveniently extremely similar to the value that the dark energy survey gets from weak lensing. So this is the well-known S8 tension, that the power that's coming out of the weak lensing surveys is a little lower than the power that comes out of Planck. And I'm detecting that, I'm detecting it at redshift 3. The nice thing about being at redshift 3 is that if you are measuring it in weak lensing, a completely plausible explanation is that AGM feedback is doing something weird. This is much less viable at redshift 3 for the simple reason that there aren't enough massive black holes at redshift 3, right? They haven't had time to form. We looked at this explicitly in a paper led by Megan Tillman, which will come out tomorrow. And this is the Simba model, which I think is roughly the strongest, pretty much the strongest viable black hole AGM feedback model that's currently around. And you can see the effect on the flux bound spectrum is very small, much smaller than the error bars of the data. I want to be clear what I'm saying. I'm not saying that this is completely insensitive to AGM physics. I'm saying that this is insensitive to AGM physics if the AGM feedback model is something that also is able to match the stellar mass function. It is possible to design an AGM feedback model that completely destroys galaxies, prevents any stars from forming. That is not a viable model, right? So that model would affect the forest, right? The way it destroys star formation is it blows up the galaxies, right? Then the gas is just spread out everywhere, right? That's not what we're talking about. We're talking about a calibrated model that can match the stellar mass function at redshift 0. And at redshift 2, those models will not have enough black holes in to strongly affect the Lyman-alpha forest, okay? Because if there were enough black holes at redshift 2, redshift 3 to affect the forest, by redshift 0, there will be so many black holes, you wouldn't have anything. Okay? For people who want to do high energy physics and don't care about the Lyman-alpha forest at all, we put this onto a plot of the effective amplitude and slope of the power spectrum at redshift 3 and 1 megaparsec, and we compared it to other probes. So this little tiny dot here is Planck extrapolated down to small scales. This is my measurement, and this is the previous measurement from the Lyman-alpha forest. And you can see that this gap here is the sigma 8 tension, is the S8 tension. There's no gap in the slope because I fixed that tension that was there before, and the error bars are a little bit bigger. Okay. So to conclude, I think I'm in time, and you get to go to coffee after my talk's finished, so I better be on time. So to conclude, what we've done is a new analysis of the Lyman-alpha forest. We had 50 large scale cosmology simulations marginalizing over cosmology. We found that there is a sigma 8 tension. It probably is not due to AGM feedback. A plausible explanation, if you just do a sort of order of magnitude back of the envelope estimate of what you would need to explain this, it will be a neutrino mass around 0.2, 0.4 eV, which I do not claim is consistent with all constraints, but it does kind of fit. If we're looking to the future of the Lyman-alpha forest, the small scale measurements that lead to dark matter constraints are kind of systematic dominated at this point, so they're unlikely to get an order of magnitude better. However, the large scales, there are new probes on large scales, there are new surveys that are able to measure larger scales, and that will provide more data in the next decade or so. So thank you very much.